Hello, everybody. My name is Tony Kučera, and I'm going to present a joint work with Jérôme Leroux and Dominik Velan about efficient analysis of VASS termination complexity. I start by introducing some technical notions needed to formulate our main results. Then I state the main results, and for those of you who stay with me afterwards, I try to sketch the main ideas of the underlying technical constructions. A d-dimensional VASS is a finite state graph where every edge is labeled by a d-dimensional vector of counter updates. In our complexity estimations, we assume that the counter updates are written in binary. A VASS computation starts in some control state for some initial counter values and proceeds by executing the edges. And such a computation terminates if at least one of the counters becomes negative. In this work, we are interested in analyzing VASS termination complexity. So what is this? So first of all, let us assume that the control states of a given VASS are divided into two disjoint subsets of angelic and demonic control states. And the computation of a given VASS is actually determined by two players, the demon and the angel, where the demon wants to prolong the computation as much as possible, and the angel wants to shorten the computation as much as possible. So we have a game of two players whose names are actually standard in the area of program analysis, and these games are determined, meaning that the usual sub-inf sub equality holds. Here the pi and sigma range over all strategies of demon and angel, I mean over all history-dependent strategies of the two players, although it can be proven easily that both players actually have simple positional strategies which are optimal. And the equilibrium value defined by this equality is denoted by T-val. So intuitively, T-val of PV is the length of the computation initiated in PV obtained under the assumption that both players, angel and demon, play optimally. In general, this T-val can also be infinite. So now we can define the termination complexity of a given VASS. It is a function L assigning to every n the maximal value of a configuration where the initial counter values are bounded by the n. Here is a short summary of the existing results about VASS termination complexity. As you can see, most of these results are relatively recent, and most of them consider purely demonic VASS, where all of the control states are demonic. So, in particular, the problem whether the termination complexity is linear, so whether it is ON, is decidable in polynomial time. And furthermore, it is known that if the termination complexity is not linear, then it is at least quadratic. The question whether the termination complexity of a given demonic VASS is bounded by some polynomial is also decidable in polynomial time. And again, there is a kind of gap saying that if the termination complexity is not polynomial, then it is at least exponential. Very recently, it has been shown that the problem whether L is bounded by a polynomial of a given degree k is also solvable in polynomial time. And if L is bounded by some polynomial, then the optimal degree of the bounding polynomial is computable in polynomial time as well. There is also a result about a slightly more general model of demonic VASS MDPs. So a demonic VASS MDP is a VASS where every control state is either stochastic or demonic. And the result says that the linearity of the termination complexity for demonic VASS MDPs with a tree-like Mach decomposition is decidable in polynomial time. And if the termination complexity is not linear, then it is at least quadratic. These results are encouraging, but they are limited to demonic VASS. And moreover, they characterize the subclasses of demonic VASS where the asymptotic growth of termination complexity is relatively low. In our work, we characterize demonic VASS and VASS games with a high asymptotic growth of termination complexity. The last thing needed before formulating these results is the introduction of our complexity measures. So we start by fixing the following hierarchy of fast-growing functions. It is almost the standard hierarchy, only that the first items are defined in the way which better suits our purposes. So this f1 is a linear function, f2 is quadratic function, f3 is single exponential function, and the next functions in this hierarchy are defined according to the following standard recipe. So fk plus 1 of n is defined by composing the previous function fk n times and applying the composition to the n. And on top of that, we introduce for every k the class gk. As we shall see momentarily, this g corresponds to Křekoščík. I apologize for my poor Polish. And this gk consists of all functions which are bounded by a function of this form. So this is fk composed with fk only constantly many times. So you may immediately observe that this gk is closed under function composition, which will be important later. As I already indicated, we call the family of gk classes the Křekoščík hierarchy. And the reason why we dare to do so is that for every k, at least 4, the class gk exactly captures the growth of the functions contained in the corresponding level of the standard Křekoščík hierarchy that can be found, for example, in the Wikipedia. So, according to our definitions, g1 contains all linear functions, g2 contains all polynomial functions, g3 contains all elementary functions, and g4 contains functions which are non-elementary. According to the previous results about demonic VASS discussed earlier, the problem whether the termination complexity of a given demonic VASS belongs to g1 is decidable in polynomial time, and the same holds for g2. Now the question is, what happens for gk where the k is larger than 2? The main contribution of our work is a precise answer to this question. For demonic VASS, we prove that the problem whether the termination complexity belongs to the class gk, where k is an arbitrary fixed constant, is decidable in polynomial time. And on top of that, we show that if the termination complexity does not belong to the class gk, then it grows at least as fast as the generator fk plus 1 of the class gk plus 1. This means that the termination complexity of a given demonic VASS can be reasonably characterized by the least k such that the termination complexity belongs to the class gk. And for the VASS Games, we show that the same problem is NP-complete, and we also prove the same kind of gap as in the previous case. Now I try to explain some of the main ideas behind these two theorems. Let me start with the results about demonic VASS. For simplicity, from now on I assume that our demonic VASS is strongly connected, and for every k and every positive integer constant mu, I use this symbol fk mu to denote the composition fk after fk mu times. To understand the termination complexity of our demonic VASS, we need to understand the complexity of individual transitions and counters. More precisely, for a given transition t or counter I, we say that the transition or the counter is beyond fk mu if there is a constant c depending only on the underlying demonic VASS, such that for all sufficiently large n's, there is a computation initiated in a configuration where all counters are equal to n, and along this computation, the number of executions of the transition t, or the value of the counter I, is at least fk mu applied not really to the n, but to the n divided by c. The next lemma says that the core of the problem is to understand the complexity of the counters. So more precisely, if I is the set of all counters beyond fk mu, then the set I easily determines the set of all transitions beyond fk mu. The set of all such transitions consists of all t's occurring in some cycle whose effect is non-negative on all counters outside I. This means that the cycle can still decrease some counters, but all of these counters which are decreased by the cycle must be in the set I. And clearly, the existence of such a cycle for a given t is easily decidable in polynomial time. The lemma is not hard to prove. The argument is based basically just on the pigeonhole principle. If we want to decide whether or not the termination complexity of a given demonic VASS is contained in a class GK, we can equivalently decide whether or not the termination complexity is beyond fk plus 1. And clearly, if the termination complexity is beyond fk plus 1, then there must be a transition which is beyond fk plus 1. And the set of all such transitions is determined by the set of all counters beyond fk plus 1. This is what we have just seen on the previous slide. So the core of our algorithm is a procedure which, for a given k, computes the set of all counters beyond fk. The procedure for computing the set I of all counters beyond fk is based on the following characterization of this set. The characterization of the condition says that the set of all counters beyond fk is precisely the set of all counters such that for every sufficiently large n, there exists a finite computation initiated in a configuration where all counters are equal to n, such that this computation pumps the values of all counters of I beyond fk minus 1, and along the computation the other counters are decreased at most by a constant kappa independent of n. This condition is obviously sufficient, because if it is satisfied, we can start in a configuration where all counters are initiated to n, and then use this sequence to pump the counters of I beyond fk. The other counters are decreased, but at most by kappa, and this means that we can restart the computation, this time for larger initial values of the counters in I, and increase them to fk minus 1 after fk minus 1 of n. And the other counters are decreased by 1 additional kappa. So this can be repeated omega n times, which is precisely what we need to pump the counters of I beyond fk. One can show that this condition is not only sufficient, but also necessary. And our algorithm for computing the set I is based on computing the maximal set of such self-feeding counters. And how do we do that? Well, at the beginning we optimistically assume that all counters pumpable beyond fk minus 1 are self-feeding, and then we try to identify a subset of these counters which are pumpable not just beyond fk minus 1, but beyond fk minus 1 after fk minus 1 of n. We may lose some of the counters on the way, and we go on by computing another subset of counters pumpable beyond fk minus 1, 3. So 3 compositions of fk minus 1 applied to n. And we keep doing that until we reach a fixed point, and the fixed point turns out to be the maximal set of self-feeding counters. It remains to explain the cleaning step of the fixed point computation. So assume that we already computed the set J of all counters beyond fk minus 1 mu, and our task is to identify the subset of J consisting of all counters pumpable even beyond fk minus 1 mu plus 1. In the first step, we identify and delete all transitions that are not beyond fk minus 1 mu. This is easy. We just apply lemma 3, and intuitively we wish to disregard these transitions because they are simply not executed sufficiently often to help us to pump counters beyond fk minus 1 mu plus 1. An important observation is that if we have a transition which is beyond fk minus 1 mu, then at least one of its predecessors and successors must be also beyond fk minus 1 mu. This is a simple application of Kirchhoff's law. So if you look at these transitions which are beyond fk minus 1 mu, they in fact form a collection of strongly connected subgraphs in the graph of the original VASS. So we obtain a collection B1 up to BL of strongly connected sub-VASSes of the original VASS. Then, for each sub-VASS BI, we compute the set Ki of all counters which are pumpable beyond fk minus 1 in BI. Intuitively, this is the way how to provide one additional iteration of this fk minus 1 in order to pump the counters contained in Ki, not just beyond fk minus 1 mu, but also beyond fk minus 1 mu plus 1. What we do, we first pump all of the counters of J beyond fk minus 1 mu, and then, when they are large enough, we run one additional computation provided by this BI in order to increase the counters of Ki even beyond fk minus 1 mu plus 1. I should say that computing the set Ki of all counters pumpable beyond fk minus 1 in BI is possible by induction hypothesis because our algorithm is recursive. So when we are computing the set of all counters beyond fk, we can assume that we can compute the set of all counters beyond fk minus 1 in an arbitrary, strongly connected VASS, including BI. Moreover, we formulate and maintain a certain assumption about the structure of computations pumping the counters beyond fk in a given strongly connected VASS. So at this moment we can apply this assumption to fk minus 1 and BI. By further modifying these computations, we show that they are usable for the purpose of pumping the values of the counters in Ki even beyond fk minus 1 mu plus 1 in the way I already indicated. So we assume that we previously pumped all of the counters in J beyond fk minus 1 mu, and then we use these modified computations to show that the counters in Ki can actually be pumped also beyond fk minus 1 mu plus 1. So by examining all of the sub-VASSes B1 up to BL, we discover certain counters pumpable beyond fk minus 1 mu plus 1 in the original VASS A. But there is one more catch. The length of the computations in BI pumping some counters beyond fk minus 1 mu plus 1 is actually about fk minus 1 mu plus 1 of n. And whenever we discover a counter pumpable beyond fk minus 1 mu plus 1, we can assume that this counter has already been pumped beyond fk minus 1 mu plus 1 before executing the computation in BI. This means that we also need to reconsider the computations in BI where the counters that are already known to be pumpable beyond fk minus 1 mu plus 1 are abstracted away, so their values are essentially replaced with the omega value. Intuitively, this is because these counters are sufficiently large so that they do not block the execution of the computations which possibly pump additional counters to the value beyond fk minus 1 mu plus 1. It turns out that after incorporating this additional observation into our algorithm, we actually discover all of the counters pumpable beyond fk minus 1 mu plus 1 in A. Here's a full algorithm. It inputs a strongly connected demonic VASS A and a k at least 3 and outputs the set of all counters beyond fk. Here's a full algorithm. It inputs a strongly connected demonic VASS A and k at least 3 and outputs the set of all counters beyond fk in A. For all k's up to 3, we can apply the results of previous works, so our recursive procedure stops for k equals to 3, and otherwise it performs the described fixed point computation, computing the maximal set of self-feeding counters. Now, let me tell you also something about the results about VASS Games. Here we have that for every fixed k, at least 1, the problem whether the termination complexity of a given VASS game A belongs to the class GK is NP-complete. The membership to NP follows by observing that the termination complexity of a given VASS game A belongs to the class GK if and only if there exists a counterless strategy eta for the player angel such that the termination complexity of the demonic VASS obtained from A by applying the strategy eta also belongs to GK. Here, a counterless strategy is a strategy depending only on the current control state. It ignores the current counter values completely. So using this result, we can design an NP algorithm which simply guesses an appropriate counterless strategy for the player angel, then applies this strategy to the VASS game A by resolving the non-deterministic choice in all angelic states according to the strategy eta, and then the algorithm checks whether the termination complexity of the resulting demonic VASS belongs to the class GK. This can be achieved in polynomial time by using the algorithm presented earlier. The NP hardness follows by adapting the co-NP hardness proof for the unknown initial credit problem for multi-weighted two-player game structures. This was observed by Krish Chatterjee, so Krish, thanks again. Let me also note that when proving the existence of the counterless strategy eta, we rely on the fact that the class GK is closed under function composition. This means that our result is not applicable to the polynomial hierarchy considered by Florian Zuleger in his recent work. And in fact, this is unavoidable. The argument, the proof, cannot be patched. We can show that although the problem whether the termination complexity of a given demonic VASS is at most quadratic is decidable in polynomial time, the same problem for VASS games is piecewise hard. At the moment, it is not even known whether the problem is decidable. Natural directions for future research include developing algorithms for termination complexity analysis for VASS games and the polynomial hierarchy. This was mentioned already on the previous slide. And also extending the results to stochastic models, so to VASS MDPs and VASS stochastic games. This concludes my presentation. Thanks a lot for your attention.